There's a crisis in the cosmos, and the fate of the entire universe depends on it. We've known that we live in an expanding universe since 1929, when Edwin Hubble first proved galaxies are moving farther and farther apart as time goes on. This expansion has come to underpin our entire theory of cosmic evolution, from the Big Bang to the formation of galaxies. The key factor is the rate of the expansion of the universe, a value that has become known as the Hubble Constant. We thought this value was pretty set, but now astronomers aren't so sure. Do we stand on the brink of a cosmic revolution? Or could it be that our entire model of the universe is wrong? I'm Alex McColgan and you're watching Astrum. Join me as we explore the crisis gripping cosmology, revealing how Hubble's greatest discovery has become one of today's most troublesome questions. For most of human history, the universe was small, or at least we thought it was. Some ancient civilizations imagined Earth to be flat and covered by a dome of stars. The sun and moon rose and set, and the constellations turned overhead. By the 2nd century, astronomers such as Claudius Ptolemy had envisioned a geocentric universe with Earth fixed at the center, and the sun, moon, planets and stars all revolving around us. This would be the reigning model for more than 1,000 years, until the 1500s, when Nicolaus Copernicus proposed a heliocentric model, where our Earth was one of several planets circling the sun, a revolutionary idea. Fast forward to the 18th century, and William Herschel mapped some of the stars in our galaxy, the Milky Way, proving that it was a vast disc-shaped system. As antiquated as it may sound now, astronomers debated for some time whether the Milky Way was the entire universe, or if it was in fact one of several island galaxies in a much larger cosmos. That is until 1923, when Edwin Hubble resolved the question once and for all. Peering through the 100-inch Hooker telescope at the Mount Wilson Observatory in California, the world's largest telescope at the time, Hubble was able to resolve individual stars in Andromeda, and within them found his first Cepheid variable. Using Leavitt's law, named after Henrietta Leavitt, who found more than 2,400 variable stars and discovered that they could be used to measure distances across the universe, Hubble determined that Andromeda was some 900,000 light-years from Earth, an astonishing distance. Too far away to be part of the Milky Way, this proved that another galaxy with its own stars existed outside of our own. Overnight, Hubble widened our view of the universe immeasurably. But he didn't stop there. He would go on to use Leavitt's law to identify 23 other galaxies and measure their distances, some as far away as 20 million light-years from our planet. Ultimately, Hubble concluded that millions of other galaxies must exist outside of our own, forever changing astronomy. But Hubble's next revolutionary discovery also needed the work of Vesto Slipher, an astronomer born on a farm in Indiana in 1875. He joined the Lowell Observatory in Flagstaff, Arizona in 1901, and between 1912 and 1925, he made systematic observations of more than 40 spiral galaxies. At the time, it was known that the light observed from these distant galaxies could be split into spectral components, and depending on what elements were present in the light source, different patterns would appear. If the object being observed was moving away, then those same patterns would be present, only they would be shifted towards the red end of the spectrum, what we call redshift. Through years of observation, Slipher found that nearly all galaxies appeared to be moving away from us, but at the time, he didn't have a way to measure the distances to these faraway bodies, let alone their velocity. In 1927, Belgian scientist Georges Lemaitre proposed a theory that the universe was the same in all directions, and that if Einstein's theory of relativity was right, it must also be expanding. But he had no evidence to support this theory, so it was ignored for the most part. That is, until we bring Hubble back into the picture. Like most scientists at the time, Hubble was unaware of Lemaitre's theory, or of another similar one proposed a few years earlier by Soviet scientist Alexander Friedmann. Instead, from the observatory on Mount Wilson, Hubble made the same observation as Slipher, that galaxies seemed to be moving away from us. But he noticed something that nobody else had spotted before. The farther away a galaxy was, the more redshift it appeared to have, meaning the faster it was racing away from us. And this was happening in every direction. More observations revealed that almost all galaxies appeared to be moving away from each other, and that the redshift of a galaxy was directly proportional to the distance of the galaxy from Earth. This was a major breakthrough. It meant that the universe must be expanding. Hubble announced his finding in 1929, and following its publication, it became supporting evidence for Lemaitre's expanding universe theory, which would become known as the Big Bang. Hubble's initial measurement of the rate of the expansion of the universe, which would become known as the Hubble Constant, was roughly 160 kilometers per second per million light years. That's about 500 kilometers per second per megaparsec. However, that number was not quite accurate, and even Hubble himself worked to refine it over his career. Since then, the Hubble constant has become a fundamental value in cosmology. We've used it to establish the age and the size of the universe, and those numbers are important for many, if not all, other cosmological calculations. To narrow in on the most precise value for the Hubble constant, astronomers have used two primary methods. But something about this value isn't adding up. When you break down the universe, there's a beautiful mathematical order to it. And that goes for everything, whether you're trying to solve the Hubble constant or figuring out how much stock you need to order to maximize your business's profits. Don't get the numbers right and your model falls apart, or your business does. But what do we do when the numbers don't add up? You sharpen your skills. Say, through Brilliant, the sponsor of today's video. Brilliant is an online learning platform that doesn't lecture, but teaches you how to think. Each of its lessons are filled with hands-on, interactive challenges, a method which is proven to be 6 times more effective at turning you into a problem-solving pro, as well as being more fun and engaging. Brilliant's maths courses help you know how to balance the equations when the numbers don't add up, exactly what you need to cut through an unruly Hubble tension. And there's something for everyone if you're experienced or a beginner. Give yourself a boost by giving Brilliant's thousands of 3 lessons on maths, science, programming, or more a try. Scan my QR code or follow the link brilliant.org/Astrum in the description. Doing so will even get you 20% off Brilliant's annual premium subscription for unlimited daily access. One way astronomers measure the Hubble constant is through additional observations of redshift. In other words, the same way Hubble made his initial discoveries. Known as the cosmic distance ladder, or late universe method, it measures the expansion as we see it now, billions of years after the Big Bang. The more examples of distant redshift that we're able to get, the more accurate the measurement should become. Over the years, this has refined the Hubble constant to approximately 73.5 kilometers per second per megaparsec, quite a bit less than Hubble's original value. The other way to measure the Hubble constant is through the early universe method, a newer technique that estimates the expansion by rewinding the clock back to the start. This relies on images of the cosmic microwave background, or CMB, an ancient microwave radiation, which is, essentially, a snapshot of the universe from about 380,000 years after the Big Bang. This cosmic microwave remnant had been predicted in 1948 by Ralph Alpher and Robert Herman. Arno Penzias and Robert Wilson detected its presence in the 1960s, winning the Nobel Prize for their work. But it wasn't until later that we got a detailed enough image to predict the age of the universe with precision. In 2003, the Wilkinson Microwave Anisotropy Probe, or WMAP, released an all-sky map that showed the early universe, a time before there were even any stars. You can think of it like this. Imagine you come from the scene of an explosion that has already happened. You see fragments strewn all over the place, and you can't make out what the original object used to look like. But then someone hands you a snapshot of just after the explosion began. I bet now you could trace each piece back where it belonged in the original image. This is similar to how astronomers use the cosmic microwave radiation to trace our present universe back to just after the Big Bang. Most recently, in 2013, the European Space Agency's Planck Cosmology probe was able to capture an even more detailed all-sky image of the background radiation, showing subtle fluctuations in temperature that would eventually ripple out to create dark matter webs, forming clusters of galaxies and voids across the universe. When astronomers take the image of the CMB and fast forward it to the present day, it's like pressing play on the video of the explosion. They get a predicted Hubble constant of about 67.4 kilometers per second per megaparsec. But you might notice this value is considerably smaller than the Hubble constant we've observed through redshift, which is a problem. I really can't stress enough how the expansion of the universe has become a pillar of our standard model of cosmology. The Hubble constant ties into our most fundamental physics, from Einstein's theory of general relativity to the idea that the universe evolved from a dense, hot, early state known as the Big Bang. Otherwise known as the lambda-cold dark matter model, it emerged in the late 1990s and has seemed to work beautifully ever since. An important feature of this model is that scientists expected gravity to slow the expansion over time, but instead, they've actually found it's now speeding up. Thankfully, this didn't break the model. Something seems to be pushing space apart faster and faster, and we believe that something is dark energy. As the universe grows, dark energy's effect becomes stronger, causing galaxies to move away faster and making the Hubble constant, the rate of our universe's expansion, increase over time. Both methods of calculating the Hubble constant are meant to give us the current rate of expansion, so it's not this acceleration that's making the results differ. But how can we have one unified cosmological model with two different values for such a fundamental rate? This discrepancy has become known as the Hubble tension, not because it represents an actual tension force, but instead, probably because of all the atmosphere it creates at cosmologists' dinner parties. And to be honest, I get it. It could mean we've got our entire cosmological model wrong. It was thought that as more accurate data was collected, these two values would converge on one agreed value Hubble constant. But therein lies the problem. As we've gotten more recent, independent measurements of the redshift, the number isn't converging. Instead, the gap is being reinforced. One independent measurement came from mega-maser hosting galaxies. These have certain molecules like water vapor that can amplify microwave radiation near a black hole at the center of a galaxy. This can create a maser, which is like a laser but with microwave radiation instead of visible light. Megamasers are extremely powerful, and their microwave emissions can be mapped precisely using telescopes. That means they can be used to measure the mass of the black hole and give a very accurate geometric distance to their host galaxy, allowing us to calculate the Hubble constant with, presumably, a very accurate distance measurement. In 2020, astronomer D.W. Pesce and others used this method to measure a Hubble constant of 73.9 kilometers per second per megaparsec, with 95 to 99% confidence. In other words, they were very sure. And in late 2024, another investigation by Daniel Skolnick, Adam G. Rees, and others resulted in a similarly shocking value. They used data from the Dark Energy Spectroscopic Instrument to study 12 different Type 1a supernovae that were dotted across the Coma Galaxy cluster around 320 million light-years away. What they found was a Hubble constant of 76.5 kilometers per second per megaparsec. Most recently, in 2025, researchers from the Inter-University Center for Astronomy and Astrophysics in India used mirror variable stars in our galaxy as anchors to measure the distance of mirror variables in faraway galaxies, a similar method to the original way of using Cepheid variables. They found a Hubble constant value of 73 kilometers per second per megaparsec. All of these measurements roughly agree, but fall far outside of the error range of the Planck measurements based on the CMB radiation. So something seems to be missing from our understanding of the universe. Astronomers, including two who worked on the DESI investigation, have been ringing the alarm bells. The paper's lead author, Skolnick, a professor of physics at Duke University, said, "Our model of cosmology might be broken," and noted that the Hubble tension is feeling more like a Hubble crisis. Without resolution, the model we use to interpret the universe rests on shaky grounds. Everything from when galaxies formed to how clusters evolve, and even predictions of the cosmic future hang in the balance. If the Hubble constant turns out to be the lower value calculated from background microwave radiation, then we live in a 13.8 billion year old universe that will likely go on expanding forever, a steady, predictable future with constant dark energy. But if the Hubble constant is the higher value observed from redshift, then our universe may be expanding faster than the current model predicts, and things may be weirder than we thought. If that were the case, then our universe may be younger, something like 12 to 13 billion years old. And it may mean that we're missing something fundamental in our understanding of the early universe, dark energy, or relativity. Some scientists have proposed that radical adjustments may be needed to reconcile the Hubble tension. These proposed adjustments have included things like decaying dark matter or dark energy that varies over time, and scientists have even explored the idea of modifying the dark energy equation of state, representing what could be a change to general relativity itself, something that may force us to reevaluate our entire understanding of not just the cosmos, but also our very understanding of physics. But another recent idea has been gaining traction, one that could save our model of cosmology without needing to rewrite physics. And all it needs to work is a little spin. No, really. The 2025 paper suggests that perhaps we've missed a very slow rotation or spin of the universe. Published by Balázs Endre Zigeti, István Zapudi, Imre Ferencz-Barna, and Gergely Gábor Banafoldi, the idea is that a very slow universal rotation once every 500 billion years would be slow enough to go undetected, but significant enough to affect how space has expanded over time. In fact, their preliminary calculations show that this slow spin could validate both values we have for the Hubble constant. When spin is introduced into the model, it predicts an early universe with a lower rate of expansion, like we get from the CMB calculations, and it also predicts a present universe with the higher rate of expansion, like we get from redshift measurements. These are exciting initial results. Zapudi, one of the idea's authors from the University of Hawaii, paraphrased the Greek philosopher Heraclitus of Ephesus when explaining the hypothesis, who said panta rei, meaning everything moves. And indeed, with how promising the initial results are, it may be true, entire universe and all. Though the authors were clear that this is just a preliminary calculation focused only on the Hubble constant. The next step towards solidifying this idea will be more complex models and simulations to check the hypothesis against other observations. I believe this idea is a reminder that there's still a lot to learn about our universe, but it's far too soon to think about throwing out our entire model of cosmic evolution, especially when we may be just on the brink of understanding the missing piece. And even if we can keep our cosmological model, it would still mean a new rotating variant of it, one where cosmic parameters and values shift to accommodate our new reality. And this idea has one other major perk. It doesn't violate any known laws of physics. Besides, I quite like the idea that not only is our planet spinning and our solar system rotating, but so too are the Milky Way galaxy and our entire universe.
Thanks for watching. If you've been enjoying Astrum's videos and want to help keep this channel thriving, I want to ask you to take less than a minute to check out the Astrum Patreon. It's not just ad-free videos, but it's a way to make Astrum's videos less reliant on sponsors and algorithms. The link is below. Your membership directly helps ensure that future videos can stay independent, high quality, and consistent, created for curiosity, not clicks. Thanks so much for considering it. I'll see you next time.